Hi, my name is Wenyaun Shi. I am a research scientist from University of Texas at Arlington Research Institute. Today, I'm here to talk about my paper, Angular Velocity Control of Numeric Soft Robotic Digits. Our hand is a complex and elegant part of the human body that allows us to perform various tasks with powerful force and high precisions. The human hand is unique, and its versatility sets us apart from other species. Hand impairments caused by injuries, stroke, or other diseases can severely affect a person's quality of life, physically and mentally. Motion therapy is a medically proven method to regain control of one's hand from impairment. Motion therapy in the form of continuous passive motion or active assistive motion has shown great success in regaining functional recovery for impaired hands. However, the traditional motion therapy requires a professional therapist to manually assist the patient to a full recovery. This is often associated with high cost, low accessibility, and not enough therapists with the given population. The picture on the right is a prototype of the soft robotic glove we have developed. Our goal is to develop a soft robotic exoskeleton that can be applied in rehabilitation setting both in the hospital and home to satisfy the majority of the hand therapy needs. The main reason we choose soft robotic approach is because it is safer on a person's hand when compared to the conventional hard robotics. The soft robotic digits were designed and fabricated in our lab at Utari. Each of the soft robotic hands consists of 5 pneumatic soft robotic digits attached on a glove. The robotic digits have actuator sections connected by solid sections as shown in the figure on the top left. The actuator sections work as the finger joints and the solid sections are corresponding to the bones connecting the finger joints. Actuators are half-bellow shaped hollow structure where the number of the bellows or ridges are different for each joint to match the range of motion that is required during motion therapy. The size of each robotic digit was tailored to match each human's finger. The number of ridges in each joint are shown in the table, where the thumb and little fingers have 2 actuator sections, while the index, middle, and ring fingers have 3 sections. The figure on the right shows the robotic digit fixed on a glove to be used for rehabilitation purpose. Flexible angular sensors were attached at the bottom of each finger. The sensor's resistance changes when bending during flexion and extension of each finger. The resistance values are individually mapped to each finger's bending angles. The pneumatic control hardware comprises of a pneumatic pump, a pressure solenoid valve, a vacuum solenoid valve, a bleed solenoid valve, 5 controllable proportional valves, 5 pressure sensors, 5 vacuum sensors, and a microcontroller. During the therapy, after the microcontroller would turn on the pneumatic pump, the pressure solenoid valve and the vacuum solenoid valve are used to switch the airflow direction from the pneumatic pump. The proportional valve is used to adjust the airflow and pressure. The bleed solenoid valve is used to deflate the remaining air in the robotic digit once the motion therapy is completed. The pressure and vacuum sensors are used to monitor the airflow. Output of angular sensors are used as feedback signals to control the soft robotic digit's range of motion. Angular velocity control scheme is used to control the robotic digit. The output of the PI controller is used to regulate the proportional valve, so the angular motion of each digit obeys the angular velocity command. The angular sensor can output the current angle of the soft robotic digit. The angular velocity is then calculated in real time and feedback to the PI controller. The system H is a dynamic model expressed by a second-order state space equation. In order to obtain the model parameters of system H, An experiment is done by giving the system an input U. The system output angle Y are acquired as shown in the next slide. Using a constant input, the same pressure is applied to each digit. The angular motion of every robotic digit was individually recorded during experiments, as shown in this figure, where x-axis is the time between 0 to 2 seconds, and y-axis is the angle from 0 to 160 degrees. Due to the difference in dimension of each robotic digit, the recording time it takes for flexion and extension is also different. Each of the 5 digits have different lengths, and so the responses for each of the recorded angle for each finger will be slightly different as well. Using the experimental data, the state space model of the system can be estimated using system identification software. In the state space equation, x is the state vector, y is the system output, u is the system input, a is the state matrix, b is the input matrix, c is the output matrix, and tau is the input time delay. Using the system identification software, the second-order state space model has been identified as shown in the table, where the identified state matrix A, input matrix B, and output matrix C are estimated using MATLAB. In order to compare the estimated system outputs with the measured data, the statistical method of goodness of fit was used. The output of the estimated state space model was compared with the experimental recording as shown in the figure on the right, where the solid blue line is the data recorded from the experiment and the red dotted line is the estimated results. The evaluation results using goodness of fit are listed in table, which shows that there are 92 to 98% of similarities between the estimated system output data and the experimental acquired data for the 5 digits. After the second state space model is built, the parameters of the PI controller are tuned in simulation, and the tuned PI parameters were programmed into the microcontroller for controlling the robotic exoskeletons. Using the tuned PI parameters, 2 experiments are conducted, and the angle of the 5 digits are individually recorded. The figure on the left shows the first experimental results. The velocity command was 60 degrees per second for flexion, from 0 to 1.5 seconds. Hold at 0 degrees per second, from 1.5 to 5 seconds. Negative 60 degrees per second for extension, from 5 to 6.5 seconds. And hold at 0 degrees per second, from 6.5 to 10 seconds. The control command was repeated 3 times. Using the flex angular sensor, there were no shift errors from the sensor during the continuous and repetitive motions. The figure on the right shows the detail of performance result of 1 cycle waveform. In the second experiment, the velocity command was 30 degrees per second for flexion and 30 degrees per second for extension, and the performance results of a control cycle are shown in the figure. The 2 experiments demonstrate the motion angular velocity of the robotic digit may be controlled according to practical applications. In conclusions, using the experimental input-output data, the second-order state space model of the pneumatic soft robotic digits was identified. The PI parameters of the controller were obtained by the simulation studies. The simulation method can decrease the manual tuning time and avoid hardware wear during controller tuning. The experimental results demonstrated that the pneumatic soft robotic digit could move according to the angular velocity commands. In future studies, with hand rehabilitation, we plan to implement this control method and evaluate its effectiveness in real-world scenarios. That concludes my presentation. Thank you for listening.